Everybody, welcome back to 3 Deviations. So in today's video, we are going to be covering coordinate optimization. So in the last video, as you may remember, we talked about oil can optimization and how we could minimize the cost of making an oil can with the most amount of volume, so least surface area with greatest volume. So that was one of the optimization problems that we've done earlier. Now we're going to do something a little bit more pure in pure math with some geometry. So this is going to be some coordinate optimization. So this entails finding a point on a curve closest to a point in space, or a point on the xy plane. So that's what we will be doing today. As always, just review differentiation and maxima and minima before you watch this video, because that's relevant here. But otherwise, let's get started. So the problem that we are going to be dealing with today is finding the point on y squared equals 2x closest to the point p 1, 4. Right, so again, it always helps to draw out a picture of what we're dealing with. And we're going to be dealing with a parabola, kind of a relation here. So it's not a function. Then we're going to have some point P. We're going to want to find the closest distance, and it's probably going to be somewhere in that ballpark. But we are going to determine exactly where it is. So what we are going to do now is determine where that point is. So to do this, we are going to need to remember the distance function. So to find the distance, we take the square root of x minus our x value squared plus y minus our y value squared. And of course, this can be 1 and 4 because that's what we're dealing with right now. And so that is going to be our distance function, but we are actually going to use the fact that we have a relationship between y and x right here to eliminate the x variable. So if I have y squared equals 2x, that means that x can be rewritten as 1/2 y squared. So we're going to use that. So we're going to plug this in here, and then we're going to write d equals the square root, still we have a big square root here, of 1/2 y squared minus 1 squared plus y minus 4 squared. Alright, so now we've got a slightly better looking distance formula, but we can do even better because we are going to square the whole thing. It's going to give us d squared equals our distance function f of y, which is going to be equivalent to 1/2 y squared minus 1 squared plus y minus 4 squared. Now that is a lot better than the whole radical that we had. So now this is the function that we need to optimize. So what we are going to do here is we are going to use the chain rule and the power rule in order to differentiate this, and then we'll be able to set it to 0 and find our values. All right, so let's do that now. So to do this, we are going to use the power rule and the chain rule, and that's going to yield df dy equals 2 times 1/2 y squared minus 1 times y, and that is going to be summed with 2 times y minus 4. Alright, so that should be pretty trivial, and again, we can rewrite this, which is going to make it a lot easier actually if we distribute this and combine as y cubed minus 8, and then we set that equal to 0. That's really easy. What cubed is equal to 8? That's going to be 2. So we didn't need to do much factoring to find our zeros there. Just a little bit of combining. So now we have y equals 2. And if we remember, so y equals 2, this is going to be one part of our answer. Now we need to find x. So if y equals 2, x is equal to 1/2 2 squared, which is equal to 2 as well, because 1/2 times 4 is 2. So now we have our point xy is equal to 2, 2. Alright, so now we have 2, 2, so that's going to be somewhere around here. Now we're going to have our distance here, and our components here. Alright, But now we can try to find our distance again, and that's going to be root 5. So now we've determined what the distance between it is. So this is going to be root 5. And we've also determined that here, 2, 2 is the closest point on our parabola to the point 1, 4. All right, so that was a pretty nice optimization problem, I think. We got to use some differentiation, we got to use some algebra, and we got to have a little bit of a nostalgic walk through some coordinate geometry, which was pretty nice. So in the next video, we're going to be back to cover some more optimization, and once we're finished, once we feel like we've done enough optimization, we are going to be moving on to the last part of differential calculus, which is going to be Newton's method. Thank you for watching. We'll see you guys in the next video. Please have a great day. See you later.